Okay, so this is the Math 2460 Zoom meeting for Tuesday, November 3rd. Do y'all have any questions this morning? Anything you wanted to see?
I was just hoping we could do the work on the next unit, the 9.7.
Okay, very good. Got a request for 9.7. I think you're going to find 9.7 pretty straightforward, and 9.8 probably a lot of gibberish. But anybody else want to have any questions or anything before we charge in? Not hearing anything. All right, so real quick on the assignments, 9.7, we got these practice problems, 9.8, page 658, these practice problems. We'll have a quiz this week. Next week, we'll have 9.9 and 9.10. That'll finish chapter 9 with a test next week. Web assign these problems, and in 9.8, those problems, email me the percent that you get correct, trying to keep it to a standard procedure here. All right, 9.7. is about something that might seem a little strange to you. Taylor polynomials. And the other name you'll see is Maclaurin. Mac polynomials. We can find the first page, 9.7. We're through our series of tests of convergence. I know that breaks your hearts. But let me try to show you where this comes from, what they're doing with this. They're just calling it Taylor polynomials and approximations. All right. The idea kind of works off your calculator. Your calculator can only do 4 things. Add, subtract, multiply, and divide. That's it. But you know that if you take your other kind of functions, like a sine of 3. Okay. So am I in radian mode? Yes. Okay. So I can punch sine 3. I get 0.1411. Now you think it's literally taking a sine, there's some magic sine function out there, and boom, it gives you this, okay? Same thing with e to the x. I can go e to the 3. Okay, I get 20.0855. Now, I hope you remember the number for e was 2.718, blah, blah, blah. So you probably think that it's taking, you might think, that it is literally taking 2.718, blah, 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 and raising it to the 3rd power. Okay, you couldn't be more wrong. If you think that. That's not what it's doing. It's not some magic sine function out there that you stick in a 3 and you get an answer, or cosine or a tangent, anything like that. because your calculator is not capable of that. It doesn't work that way. It can only add, subtract, multiply, and divide. Oh boy, now I'm getting personal. Golly, okay, yeah, okay, didn't mean to do this. I don't know how to get rid of it. Let's see, can I go back to this? Get back to the camera. Okay, are we back to the camera? Can y'all see the camera? Okay.
Yeah.
Okay, yeah, you just can't do that. It can only add, subtract, multiply, and divide. So there's not, some magic sign. It's not taking 2.718 to a third power. You can't do that. The only formulas that add, subtract, multiply, and divide are, and we want to take a stab, it starts with P. Polynomials. X squared minus 5x adds 6. 3x cubed plus 4x squared, your standard polynomials. Your calculator is using polynomials to do this in any higher function. I don't hear any oohs and ahs. The natural question, how is my calculator using polynomials to do this? You all are so awestruck, I can't hear anything. You're struck that, gee, my calculator. Yeah, you ever sat around, how's my calculator give me sine of 3 when it can only add, subtract, multiply, and divide? It's
All the time.
Oh, yes, absolutely. Your calculator is using polynomial approximations to sine, cosine, we can list them, I probably can't list them all. Any higher order function, I meant tangent, e to the x, log, sinh, all those hyperbolics, they were in 5.9, arctangents, arcsines, arccosines, blah, 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 blah. And a guy named Taylor figured it out in the 1800s. So the scheme was figured out by Taylor, English guy in the 1800s. I'll show you the scheme. It reads like a whole bunch of gibberish. But trust me, once I show this to you and show how things are plugged and chugged in, it's really the easiest problems you're going to do all chapter. Trust me. Now, what happened is a Scottish guy, Maclaurin, came along and put C as 0 in, and they technically call, when you do that, the Maclaurin polynomial. So you'll see both names used. Maclaurin was Scottish, of course. Taylor was English. Now, if you guys know your history, you know that the English and the Scots have not exactly always gotten along very well in human history. Have you all ever seen Braveheart? Mel Gibson? Probably came out before y'all were born. I think it came out in 1995. You ever happen to?
Movie.
What now?
It was a great movie.
Great movie, yeah. So if you've watched that movie, you know that the English and the Scots have not always exactly gotten along real well in human history. But in any case, they give Taylor the credit for the general scheme, and Maclaurin, if you put in C, is 0. All right, now I'm going to write it out. This is called the Taylor polynomial. Okay, f of c plus f prime of c x minus c. By the way, this is centered at c. The book in the homework will ask you to tell what things are centered around. See how it's kind of college algebra, you stick in, x minus, you're shifted right. If the c happens to be negative, then you wind up with minus negative c, and then you'd be actually shifting left. All right, plus f double prime of c x minus c squared over 2 factorial. Yep, this is where the factorials come from again. I'll write out a couple more terms. The third derivative at c x minus c cubed over 3 factorial. This will be a third order, and it goes it goes on to fn, the nth derivative, terminates in this section. We're going to redo this in section 10. They'll call it Taylor's series, which implies it goes to infinite, and you add on dots. Fn of c x minus c to the nth power over n factorial. All right. Unfortunately, Maclaurin kind of gets shortchanged. We kind of almost generically call them all Taylor. Pn of 0, c equals 0. If you'll have f of 0. Actually, this should still say an x. You're putting the c equals 0, not x. Plus f prime of 0 x. It shortens it up, in other words, plus f double prime of 0 x squared, because x minus 0 is over 2 factorial. They call these the coefficients. If you wanted to put a 1 factorial, you'd find, but they never do, because 1 factorial is just 1. All right, plus, and you'd have f triple prime of 0 x cubed over 3 factorial. This would go on to f n, the nth derivative of 0 x to the n over n factorial. Okay, I know it reads like a lot of gibberish, but it really honestly is the easiest problems. The only thing you got to be able to do is take derivatives. I hope you remember all your derivatives from Calc 1. That's why I was trying to say at the beginning of the chapter, a lot of chapter 9 is straight Calc 1. We'll try try to show you what's going on. We'll run through example 3. Maybe, okay, example 1. Example 1, f of x is e to the x. We're going to show you exactly what your calculator is doing. It is not doing 2.71a, blah, 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 raised to the x power. But that's the way you think of it. And I think of it that way too, but it's not. Okay, so in other words, I'm going to run through what it's actually doing for e to the x, and they're trying to run through exactly what your calculator is using. Okay, we're going to find several polynomial approximations. These technically are Maclaurin polynomial approximations. All right, I'm going to plug and chug into the formulas on the previous page. I'll rewrite it. F of x is e to the x. It would be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial. I'll take it out to the third, x squared plus another one, f triple prime factorial x cubed. All right, let's call this number 1, number 2, number 3, and number 4. Okay, so number 1, f of 0 is e to the 0, which is just 1. So I'm constructing a polynomial across, and the first piece is 1. All right, let's just do that one. Hopefully you remember what e to the x looks like. y-intercept's at 1. And what this says is your first approximation is y equal 1 right here. You can see this on the calculator. Let's see, graph, okay. E to the x, and then just 1. There's e to the x, and there's 1. And you see how you get absolutely perfect agreement, but at one spot, one x value. You get perfect agreement right there. But you see how you move off of 1 and the curves diverge? This means e to the x is doing this, but my 1 isn't working anymore. You get the idea?
Yeah.
So let's try to widen the area where we get agreement. So we're going to add in piece 2 there. So f of x is e to the x. F of prime of, that's why they picked this easy example, is also e to the x. When you do derivatives, e to the x doesn't change. And you need f prime of 0 is e to the 0, which is 1. So in other words, this is my, say, second order approximation. F of x is e to the x. See, now I'm plugging checking. My f of 0 is 1. F prime of 0 is 1 and times x. In effect, 1 plus x. All right, let me put that on. I'll take the 1 off because you start overlaying too many of these and it just, let me shorten the y window a little bit. Let's make it -2 to 2. And y equal, let's take off 1, well, or just add on. I'll just add on 1 plus x. Let's see. All right, there's e to the x. Okay, can you tell, maybe I should use a little bigger y. Let's make that 5. All right, there's e to the x. Okay, can you tell you get just a little wider agreement? You can see when the graphs kind of coincide, you're getting much more agreement. So they're using 1 plus x to approximate e to the x. Is this as clear as Lake Lanier?
Yeah.
Okay, let's add on another piece. So as you add on more pieces, you get a wider and wider area. If you wanted to, getting a wider and wider area, 1 plus x, sorry about the x. So let's add on a third piece. So f of x is e to the x. I know f prime from this, f prime of x is e to the x, so f double prime of x is also e to the x. F double prime of 0 equals 1. So plugging these pieces in, e to the x then is 1 plus my 1x. And then f double prime, I get 1 plus 1 over 2 factorial x squared. F double prime of 0 by itself is 1. I'm divided by 2 factorial x squared. Clean this up and I get 1 plus x. 2 factorial, remember, is 2 times 1, so that's a half x squared. All right, I'm going to compare e to the x and just this. All right, so I'm going to add on a plus 1/2 and x squared. So there's my e to the x. And you can see I'm getting pretty good agreement along from here to here, not so much over here. But the whole point of this is that as I add more and more terms, I'm getting better and better agreement with e to the x. Do you want to see one more piece, or are we getting the idea across? And we can just jump to, so we're 20 minutes in, jump to some homework examples.
I think we can start with some homework examples.
Okay. If you run to the homework, they give you a whole bunch of stuff at the earlier that I skipped. I believe I started at 17. They give you a section of Maclaurin. Give you a section of Maclaurin problems. They tell you how many pieces you want to go out to x to the fourth, x to the fifth, et cetera on some of these. And then they jump more generally to Taylor. I think this is the only two sections I gave you. And they give you C values. I can do one. I don't know if I get time to do one of each. I guess we'll charge into 17. Soft page 648. F of x is, they give you a coefficient e to the 4x. Tell you n is 4. Find the Maclaurin polynomial. Find the polynomial. Okay, I like to go ahead and write it down so I know what I'm plugging and chugging into. So I am plugging and chugging into f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial, f triple prime of 0 over 3 factorial x cubed. I guess I ran out of room for the last one, plus f fourth derivative over 4 factorial of 0 x to the fourth. It literally is plug and chug. The easiest way I use is to just make a table. So I start over here with the first column with f of x is e to the 4x, and I'll need an f of 0, e to the 4 times 0, that's still e to the 0, which is 1. And now I just go down the row or down the columns really, for each of these other pieces. See, I need an f prime of x. Can you see that that's going to be e to the 4x with a chain rule of 4? Then I need f prime of 0. In other words, it's a process. Just take a derivative, plug in 0. Take a derivative, plug in 0. So you filled in all these pieces. Is going to be e to the 4 times 0 times 4, which will be just 4. E to the 0 is 1 times 4 is 4. All right, should we pause for station identification? Are we losing anybody?
Oh, we good.
Okay. Next derivative then. You're going to have a 4 e to the 4x times another 4. Or if you want to do it down here, 16 e to the 4x. Because every time you do a derivative, you get a factor of 4. Do f double prime of 0, plug in 0, you'll get 16 e to the 4 times 0, which will be just 16. Two more pieces to go. F triple prime of x will be 16 e to the 4x times 4. That'll be 64 e to the 4x. And you see your f triple prime of 0 is then 64 e to the 4 times 0 would be 64. Are we losing anybody? Everybody's so awestruck, you're...
That all makes sense up to now.
Okay, one more. Fourth derivative would be 64 e to the 4x times another 4. And I don't know if you all are a genius, whatever 64 times 4 is. It's 256. You can see the pattern. When you plug in 0, your e to the 0 goes to 1, and you get whatever that coefficient is, 256. So f fourth is 256. Are we ready to plug in chug?
Yes.
All right, one thing about it, people do get a little confused. The only place x should appear in my final formula here is right here. These little gibberish here, these are just numbers, coefficients. No x's should appear here, 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 here. The only x's are this polynomial where you get these powers. No x's here, 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 and here. No x's. That's the only way to screw it up. All right, are we ready to plug in chug? Okay, e to the 4x is supposed to be equal to, start with f of 0. Oops, that was 1. See if I can get both. Okay, got a 1 for that piece. F prime of 0 was 4, so that's plus 4x. 4 for this times x. Are we losing anybody? It really couldn't be simpler once you see a couple of them done. So f double prime of 0, that's 16 over 2 factorial x squared. Your f triple prime of 0 is going to be 64 over 3 factorial x cubed. And your f fourth is 0, that's the 256 over 4 factorial x to the 4th. So to compute an e to the 4x, your calculator is plugging into a polynomial that looks like that. Oh boy, where'd that come from? Can you read that? Okay, it went away. Now, I'll warn you, look in the book and you probably don't see this. My guess is they simplify these coefficients. But let's, if you're fascinated, let's take a look. It's 17 out of 9.7. They did simplify it. Okay, now the 4x is still there. Okay, here we are. We've got the 1 plus 4x. But they simplified the rest of them. Y'all dying to see how those simplify? Maybe I can show. If you remember, 2 factorial is 2 times 1. That's 2. So there's an 8. 1 plus 4x. 16 divided by 2 is an 8x squared. You'd have 64. 3 factorial is 3 times 2 times 1 x cubed. And 256 is 4 over 4 times 3 times 2 times 1 x fourth. So 2 into 64 leaves 32, and 256 divided by 8. Divided by 8, you're at 32, yeah, 32 over 3. So boom, boom, you have 32. Yeah. So finally, and again, you're just on the test, you're just going to grade me. You're going to have a 32 over 3x cubed and a 32, both? Yeah, it is 32 over, both of them work out 32 over 3. And that, yeah, that's what the book has. If it would clear up, focus in. Yeah. Questions about that?
Nope.
All right. Anybody want to see any more Taylor? I'm sorry, that was a Maclaurin. Any more Maclaurin, or you want to see a Taylor?
I think we can get to a Taylor.
Okay. Maybe I'll do the first one, 2 over x. Page 649. F of x is 2 over x. N is 3. C is 1. You see why they can't use 0? You can't do a Maclaurin on this. That would put in, you'd be centering around 0, and x is 0, you'd be blowing up. All right, so find the nth Taylor polynomial. Their directions. And that Tom Square is trying to focus in on it. Okay. Once again, I like to write out exactly what I'm plugging and chugging into. See what kind of useless, see if I can write it out from memory. You would have, remember this is the power. You can't confuse the N and the C. So what you would have is you'd have f of c plus f prime of c, I'm using generically, x minus c. See, this is n equal 1. See, so I got to go out to n equals 3. You'd have f double prime of c over 2 factorial squared. So I'm at n equal 2. So I'm at n, and I got to go to n equal 3. So f triple prime of c over 3 factorial x minus c cubed. All right, if you want to go ahead and plug in c equals 1, this one's going to go in f of 1, f prime of 1, x minus 1, f double prime of 1 over 2 factorial x minus 1 squared. I lost my room for my third one. Plus f triple prime of 1 over 3 factorial x minus 1 cubed. What you're centered around is the x value that makes these 0. So on a Maclaurin, when you had f double prime of 0 over 2 factorial x squared, see x equals 0 makes this 0. That's, you're centered around 0. Here you're centered around 1. Because 1 minus 1 makes these 0. Any questions so far? I'm now ready to make my table and plug in these pieces. Y'all are so awestruck, no one can speak. Are we ready to plug and chug?
Yep. Yeah.
Okay. All right, well, your f of x is 2 over x, so your f of 1, that's this first piece, is 2 over 1, which is 2. This one's going to be a matter of take a derivative, plug in the c value, which is 1. Last one was take a derivative, plug in 0, and that's what you do on all Maclaurins. This one's going to be plug in 1. Take a derivative, plug in 1. And plug it in 1 into all these derivatives. They have to give you that c value. Maclaurin, they don't tell you. Maclaurin just assumed to be x equals 0, or c equals 0, actually. All right, next one, f prime of x. See, you can write this as 2x to the negative 1. So you got a negative 2x to the negative 2, which is negative 2 over x squared. F prime of 1 would be negative 2 over 1 squared, which would be negative 2. That's a 1. See, then you want to bring this back. To do the next derivative, you want to bring this back up. That's negative 2x to the negative 2. Or actually, you got it here. Yeah, I didn't have to do it again. Sorry, you got it right here. Are we ready for the next derivative? So f double prime of x would be a positive 4, x to the negative 3, which is 4 over x cubed. F double prime of 1 would be 4 over 1 cubed is 4. And we're going to go for one more. F triple prime of x would be, yeah, see, I use this form, negative 12 x to the negative 4, which is negative 12 over x to the 4th. And so f triple prime of 1 would be, can you tell, negative 12. Negative 12 over 1 to the 4th. Well, let me write it, which would be negative 12. So yeah, I highly recommend creating this table, writing out the formula you're plugging and chugging into, writing out this table, and then plug and chug the pieces in. Couldn't be simpler. Are we ready to plug and chug the pieces in?
Yeah.
Okay. In effect, 2 over x then is approximated by your f of 1, 2. All right, this is 2. Your f prime of 1 by itself, this is a negative 2. So you can go plus negative 2 if you want. And then x minus 1. Your f double prime of 1 right here is 4. So that's plus 4 over 2 factorial, x minus 1 squared. And your f triple prime of 1 right here, negative 12. Minus 12 over 3 factorial, x minus 1 cubed. If you want to clean these up, this is 2 and this is 6. 3 times 2 times 1. So 2 minus 2, x minus 1, plus 2, x minus 1 squared. 4 divided by 2 is 2. And minus 2, x minus 1 cubed. I don't know if that pattern of adding, subtracting 2's holds. Let's see. This was 27. Yep. Looks like that's what they've got, if it'll focus in. 2 minus 2, x minus 1, add 2x minus 1 squared minus. My guess is that the plus 2's minus 2's alternate all the way through on it. Those patterns usually come up and hold. That's about all we can show you for 9-7. You want to see any more? I'll warn you, 9-8 is going to be a lot longer and a lot tougher. But I'm willing
Could
to
we
stay
maybe
as
have an
long.
introduction?
Sure,
Could we have an introduction to 9-8 and then maybe finish it on Friday?
sure thing. 9.8. Title is called Power Series. Kind of comes out of the blue. They're kind of generic. Like this section kind of comes along like pure gibberish. Like, where did they get this stuff? Power series literally is a series of powers. And it really comes from the geometric. Y'all remember your geometric? 9.2? It's some n equals 0 to infinity of a r to the n. And you got a plus ar squared cube, blah, blah, blah. And remember, for r less than 1, you got an a over 1 minus r. This ring a bell, or is this like whoosh?
I remember.
Okay. Well, this is your power series. When they do this. Now, you can twist it around. And your A over 1 minus R can be written as A plus AR plus AR squared plus AR cubed plus AR to the fourth. Again, R less than 1. This is the function that this expands to. They don't like using R. So they make R equal X. And in 9.8, they are only going to work on this right side. And they're not going to tell you what it represents or what it approximates. And that makes 9.8 a whole bunch of gibberish. What it approximates. So in 9.8, you're going to see A plus AX plus AX squared plus AX cubed plus AX to the fourth, blah, 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 blah. That's called a power series. And it can be expanded back to summation n equals 0 to infinity of a x to the n. And it gives you a 0 plus, they're going to allow for different coefficients. Back on the geometric, they were all the same, a constant a. But they're going to allow for different coefficients, plus a 2x squared plus a 3x cubed, and so on. And that is where they get this. Now, again, with a straight x, a 0 makes those individually 0. So this one is centered around 0. But if they do this, I should have an a in there, an x minus c to the n, now you're centered around c, because c minus c would be 0. It's the value of whatever makes this 0, that's what you're centered around. That would expand out a0 x minus c, I'm sorry, that's just an a0. a0 plus a1 x minus c plus a2 x minus c squared, a3 x minus c cubed, and so on. And that's where they get their second row, if it'll go in. Okay. Well, what they're going to want just in this section, they're going to want you to find the x values where these, keep them both on the pin, where these converge. In college algebra, there's a very simple name for that. They call it the domain. It was called the domain. Naturally, we can't call it the same word here. That would be too simple. Here, we call it the interval of convergence. And there will literally be an x min and then x max where these converge. I very cleverly abbreviate this IOC. Now, what's going to make this really technical, I hope you remember your interval notation. You all remember your interval notation? See, as math teachers, we have this fantasy that when we tell you something like way back in college algebra, you remember it perfectly for life. Is that true, or does anybody want to destroy my fantasy?
Sorry to break it to you, but no.
Okay. Those, there's 4K, just to remind you of this, because they're going to get very technical with this. 4 cases, I'll use numbers. Let's say you go between 3 and 5. 3 less than or equal to x less than or equal to 5. Well, your interval notation, they write 3 comma 5, and they're going to use brackets for or equal to's. All right, case 1. All right, say case 2, let's say you don't use 3. So that's going to use a parentheses 3 comma 5, but then keep the bracket there. Is this ringing a bell?
Yeah, kind of, yeah.
Okay. All right. Third case, let's say you use the 3, but not the 5. So you'd have bracket on the 3, 5, but a parentheses on 5. In the fourth case, you don't use either one. That case, you put both in parentheses. So this means an interval between 3 and 5, numbers between 3 and 5, not including 3 and 5. Up here, between 3 and 5, but you're including 3 and 5. Here you're including 5, not 3. Here you're including 3, not 5. All right, this is going to come up all through this section. Now, they're also going to have you find what's called a radius of convergence. Now, if you graph this out, you can see it's almost like a circle. Let's say between 3 and 5, your middle would be 4, and your, call that the ROC, radius of convergence. Your radius of convergence is the distance from the center out to one edge. So your ROC runs from here to here, and your ROC would actually be 1, the distance between 4 and 5. The very first section of problems, I call this a half problem. You kind of get this halfway through a full IOC problem. The IOC is your full problem. This is a full problem. You find this and can get this halfway through. So in the section of ROC problems, you're kind of quitting halfway through. They're using radius like it's a circle, distance from the center out to one edge. That's basically the buildup. I tell you, C1, it's all gibberish, I understand. Have you got the patience? We're almost 50 minutes. You got the patience for a quick examples?
I am, but yeah, I am.
Okay, yeah, if everybody needs to drop off, help yourself. I mean, I can't see. It actually starts really simple. Here's the homework. I know it's a lot to throw at you in one session. Page 658. Really simple. They just want you to tell what's centered around. State where you're centered. Well, I hope you can tell, instead number 5, that's a straight X. So you're centered at 0, because that 0 makes that X 0. Can you tell where you're centered here? What would make X minus 2 0? It would have to be 2, right? So that's all they want there. Couldn't be simpler. So yeah, at 5, you're centered at 0, 7, you're centered at 2. That's all they want. Okay, notice they give you 3 odd radius convergence problems, and these are kind of like half problems compared to these. Down here from 15 to 37 here, and I didn't go all the way to 37, I think I quit at 33. Interval of convergence, check for convergence at the endpoints of the interval to really nail stuff down. These are projects. So do you want to see, I can show you number 9 and show you the radius and then finish it and find its total interval of convergence.
Yeah, how about let's do one of the easier ones today, and then we can do one of the big ones on Friday.
Okay. How about I charge into number 9 and I'll just do exactly what they asked for. And then rather than start from scratch on one of these, I can finish it up with an interval of convergence just to show you what that's about.
Okay.
Maybe we can try it that way. All right, so number 9. Page 658. Here's the gibberish. -1 to the n, x to the n over n plus 1. The directions are find radius of convergence, all abbreviated ROC, radius of convergence. Just, I like to show people what these look like expanded out. The problem is they're not going to show you what it approximates. So expanded out, you're looking at n is 0, see this will be a positive, x is 0, you'd be 1 over 1. All right, so that's n equals 0 plus, or if n equals 1, you're a negative x over 2. And then if n equals 2, you're back to positive again. -1 squared would be positive, x squared over 3. And then you see the pattern. You'd be a negative x cubed over 4, positive x fourth over 5, etc. But they're not going to tell you what that approximates. They just want to know what x values will it converge. That's what ROC and IOC mean. What x values will it converge? All of these problems are ratio test problems. That's what you use. I'm thinking text, you use. Y'all remember your ratio test. That's why they showed it to you, 9-6. Ratio test was to take a limit as n goes to infinity, the absolute value of your an plus 1 over your an. Okay, I'll like speed this up. And by the way, you ignore this. It's not part of the term, it's just sign switching. Your an plus 1, okay, so you got a limit as n goes to infinity. You've got x to the n plus 1 over n plus 1 plus 1. I'll write it all out. Divided by your nth term is your x to the n over n plus 1. Are we losing anybody? Everybody's so awestruck.
I'm currently good. Yeah.
Okay. So you have a limit as n goes to infinity. You'd have your x to the n plus 1, your top, over n plus 2, 1 plus 1 there, times, and you flip your bottom, n plus 1 over your x to the n. So you're multiplying by this and you flip. Collect your terms. You can remember that's x to the n times x to the 1. I'll collect the x to the n under it. And you have n plus 1 over n plus 2. Are we losing anybody? That's an x to the 1, my fault. Tough enough without me screwing up. It's x to the n times x to the 1. Are we losing anybody?
Nope.
See, your x to the n's cancel. You're left with this x, but all you care about is what the n is doing, and that's over here. So can you see you get an infinity over infinity? Can you see how the L'Hopital rule is going to work out? Your top derivative is 1, your bottom derivative is 1. So you're getting a limit as n goes to infinity. You get an x, and basically you're getting a 1 over 1. Top derivative is 1, bottom derivative is 1, which means you're getting an absolute value of x. See, you have no n in here to plug in, so you're coming out x. Now this is where it's slightly different from 9-6. In 9-6, you came out a number. Remember, if that was less than 1, you converged. Greater than 1, you diverged. Equals 1, no idea what was going on. So what you want to do here is you want to set less than 1 to converge. So we're going to set less than 1, and we're going to have convergence. Now, this is where your college algebra comes in. If you've got absolute value of numbers that are less than 1, they got to lie between -1, less than x, less than 1. Which means on the number line, they're between -1 and 1. Are we losing this? See, if I have a negative 0.8, absolute value of it's 0.8, still less than 1. You're between the negative of this and positive of this on the number line. We losing anybody? You may not be able to hear me. It just went unstable. Can you hear me again?
Yeah, it's better. Yeah.
Okay. Everybody see, you're kind of laying out. You're going to, however your ratio test works out, you're going to set it less than 1. Some are more complicated. This one's easy enough. It's a straight X, but some are more complicated further down, trust me. And so you're going to lie between -1 and 1. You can now get your ROC. See, 0's in the center. Your ROC is 1, and that's all they asked for. Distance between 0 and 1, your ROC is 1. And that's all they asked for. And if you wanted to quit and do exactly what they asked for, you're done. That's why I call this a half problem, because if they wanted to IOC, we've got another whole page of gibberish to go. But it'd be a lot easier doing that just to show you an example rather than starting from the beginning. So you game, we're at about an hour. It'd probably take another 5 minutes to finish, maybe even less. See how an IOC example works?
Sure.
Okay. What we have with this number line, I call it the nominal IOC. You basically have between -1 and 1, but you don't know what happens at the endpoints. What happens? Remember the 4 cases at end points. Which of the 4 cases is it? Does it look like this? You're -1, 1. Does it look like this? Does it look like this? Or does it look like this? You see the dilemma? I know you're dying to know. The suspense is killing me. I'm dying to figure it out. This is called checking at the endpoints. And it's what turns it into a project rather than a problem. What you got to do is literally plug in x equals 1 and -1 into the series and write it out. So the original looked like, okay, sum of n equals 0 minus 1 to the n, x to the n over n plus 1. I'm going to check. The order you do it doesn't matter. I'm frozen. Can I get back? X equals 1. Let me stop. See if we can get it back, if I got to break it. I'm so close. God, I know you're dying. I know the suspense must be killing you. So what you do is you plug in sum minus 1 to the n, 1 to the n over n plus 1. There's no, unless you're a real genius, there's no way to tell what is going on just from this. You really need to write out your terms. A lot of these are harmonic. Remember, a straight harmonic with all the same signs converges. If it's alternating signs, it diverges. So I hope you remember all that. If written it out, see, I subbed in x is 1. I get, if n is 0, you get a positive 1 over 1. If n, that's n equals 0, all right? And then if n is 1, you actually get a negative 1 over 2. It's n equal 1. All right, n equal 2, positive 1 over 3. If n equal, I'll write out one more. Negative 1 over 4. That should be enough to show you. You see the first power? First power. This is harmonic. So now it depends on what the signs are doing. Can you tell what the signs are doing? They are clearly what?
Alternating.
Does that mean it converges or diverges? See if anybody remembers.
Converges.
This means it converges. So x equals 1 is in the interval of convergence, in IOC, interval of convergence, meaning it's either a case like this or a case like this. It's not this or this. So now I've got to nail down x equals -1. This side. Is -1 in or out? The suspense is killing me. Let's find out. So we're going to check x equals negative. This is what you got to do on a full IOC problem. Okay, so you'd have sum n equals 0 to infinity, -1 to the n, -1 to the n again, because I'm putting in -1 for that x, over n plus 1. Now you could play around with this. It'd be a -1 to a 2n. Yeah, if you want to help yourself. I just write out the terms and I'm looking to see if they're the same sign, alternating signs. So n is 0. You're going to get +1 over 1. That's n equals 0 because these will both go to 0 powers or 1s. 0 plus 1 is 1. Okay, and n equals 1. You're going to get a negative times negative, meaning you're going to get a plus, a -1 to the 1, a -1 to the 1 over 2. You're going to positive 1/2. It's going to be a 1/2. N equals 2. Both of these will be positive. Squared and squared over 3. So +1 over 3. N equals 3. Again, a negative there. A negative still is positive over 4. Can you tell all the signs are the same? Sign's the same. Does that mean it's harmonic? You tell me, converge or diverge?
Diverges.
Very good.
So it's the second option.
Second. So IOC is this one with a bracket. Now you won't find that answer in the back of the book because it didn't ask for it. But that's what it takes to do a full IOC problem, which you're going to have to start at problem 15. Okay, we are at over an hour, so your patience may be wearing thin. Oh, we still got everybody. Hard to believe. Yeah, so it's actually this. Our suspense is over. I now know. In college algebra, we called that the domain. But that's how you find, they want you to find it here. They call it this interval of convergence. And it would not include -1. It would diverge at -1, but include every number up to 1, including 1. That's a lot of stuff to throw at you, but that's basically everything you need in both sections. Next Zoom meeting will be Friday. Is there anything else we can help you with?
Nope. Thank you so much.
All right. Anybody else have anything you want to say? I'll just tell you, if you're out there going, whoa, why did I sign up for this class? Chapter 10, much easier than chapter 9. Chapter 10 is so easy, I don't even have a review sheet for it. It's all calculated work. Don't even need a review sheet. It's that easy. So chapter 10, we end with a much easier chapter than this. I don't know if that makes you feel any better or not. Probably not. Are we ready to end the meeting?
Yep.
All right. Thank y'all for coming out early today, and hopefully we'll see you on Friday. Thank you.
Thank you.
Thank you.
Thank you.
Richard didn't know she was in the hospital either. I'll monitor it. Yep. I guess from Canton.